G'day, welcome back. Today I'm starting a new video series which I am calling Rabbit Holes, where I cover some chess related topic in way too much detail. So the topic for today was inspired by my previous video, which I had called Chess Engine Tuning Out of Order. And in that video I showed that the move ordering function of Stockfish had an enormous impact on the strength of the engine. In brief, if you fed the orders in sort of a sensibly ordered way into the alpha beta pruned search tree, you could actually gain a couple of hundred points of ELO strength because the number of nodes the engine was considering was reduced by a substantial margin. So having done that video, I decided I needed a bit more research to understand better how alpha beta pruning works in terms of reducing the number of nodes. And then secondly, what sort of impact does the move order have? You know, the best move order, the worst move order, random move order, or indeed, what impact do things like the branch factor of the tree and the depth of the tree have on it, right? So a lot of things to investigate, and that's why it's a really deep rabbit hole today. Now, the starting point, just having a quick look at the alpha beta pruning page on Wikipedia. There's a lot of interesting stuff on this page, and I found particularly interesting the references. There was David Knuth, a famous guy in computer algorithms, was mentioned in terms of refining the alpha beta algorithm. And if you go down to the references at the bottom, there's actually an article by David Levy, and he was one of the early pioneers of chess computing. So that means that this has been a topic of investigation even since the very early days of computer chess. And what I'm going to come up with today is just an updated summary of all these factors which go into, move ordering and alpha beta pruning. So what we're going to do first is look at a few examples of alpha beta pruning using Python and some visualization. Okay, here we are. At this stage, you realize you need Brady Haran from Computerphile. Anyway, so this is a little visualization tool which I put together using Graphviz and Pygame within Python. You can see this is a simple binary tree, depth of 4. The black circled nodes are the maximizing ones, and the red circled nodes are the minimizing ones. So let's see how the alpha beta search works in this case. Okay, the green circle is the one you're currently evaluating. You've got down to the leaf node, no further to go. So that will give a value of -1 to the node above it, which is a maximizing node. And you can see that alpha beta algorithm keeps an alpha value, which in this case is -1, which is the best value which the maximizing player can get at this stage. As -1 is not very good. And then the beta, which is set to positive infinity, the beta is the effectively the best score which the second player has. Okay, so now we go to the 3 node. That's better than -1. So now that node gets set to the value of 3. We go back up the tree to the node above, and then now we have to search down its other child. Now we get to this value of 5, right? So you then set 5 to the node above. 5 is bigger than 3. 5 node is a maximizing node. It doesn't matter what's in the right hand leaf node anymore. It'll be 5 or better because it's a maximizing node. And you have a look at the value on the minimizing node above, the red one. It's already got a 3, and you can see the beta value is 3. So actually, because this value of the 5 node is going to be 5 or better, then there's no need to look at the 1. The minimizing node above automatically pick 3, and that's what's happened, right? So as you go through these nodes, you compare the current node value with alpha and the beta at different points, depending upon whether it's a minimizing or maximizing node, and you can drop nodes out. So we didn't have to look at that one node at all. Okay, so now we've got a value of 3. We go back up to the maximizing node, and now we go down this minimizing node, maximizing node, -6. Okay, so -6 is not particularly good. -4, also not particularly good, goes to the node above. Now, what you can see now is that value is -4. And it's pretty obvious that because -4 is, it's going to be -4, it's going to be even worse than -4. Maximizing player is already guaranteed a value of 3. That's the alpha value. Because -4 is less than that, that's where you cut off a whole branch, right? You didn't need to look there because you could only get less than -4 wouldn't be chosen. So that was just the first example I wanted to go through, and you can see that actually you've saved 4 nodes doing that, right? You didn't have to look at 4 nodes, which you think could be a very expensive operation. It could be, you know, neural network evaluation, or even just a static evaluation. So by we've saved about, you know, 25% of the work by doing the alpha beta pruning on this example. So let me just quickly move on to another example. Okay, here's my second example. Same as the first example, just the leaf nodes are different, just to sort of show that, you know, you get different results depending upon the leaf nodes and the way they come in. Okay, we go down the left-hand side, we go to 5, 3, so I'm maximizing, so that becomes 5. And then you go back up to the minimizing node, and the minimizing node realizes that this maximizing node below it will at least have a value of 7. And once again, look at the alpha and beta in the top corner there. 7 is greater than 5, so we just cut there and go back up, and that value is 5, right? We saved 1 node already, and then we go down to the right-hand side, get a 4 and a 6. So minimizing node, value of 6, we have to trace here 8, and now we get the same situation. That's an 8. It's going to be at least 8, so that means the node above 6 at best, and then now you just maximize and the value of 6. So it's pretty quick, but you can step through these trees and you can see how the alpha and beta cutoffs are reducing the number of nodes you need to cover. This only cut off 2, but you know that's better than nothing. So now we're going to do the same analysis, but we're going to go 1 level deeper. Okay, here we are. You can see it's getting much wider, even though I've made things a little bit smaller. Now you can see the top node is a minimizer node here. So let's just step through the tree, go up down the side to 0, maximizing. So that's 0. And then we now go into the sub tree of this minimization tree. And then now we've got 9. So that's going to be 9 or more. That the value of that node with leaf with 4 in it doesn't matter. So it's going to be 9 or more. Obviously the minimizing node red would not choose that way. So the 4 gets skipped. Okay, that's good. Save 1 square. So now we're maximizing here, minimizing here, maximizing here. So we're going to get a 5 up there after we've done that. And we're minimizing here. Okay, 0. That could still be lower, so we have to go and check that. So it's going to be a 1, and that's going to be a max. It's going to be 1. Okay, right. So back up to the root halfway through. Let's go down this side. Maximizing this, so that's values 4. And first value we get there is 8. So that means that maximizing node is at least 8. The minimizing node above it, it's not going to choose that way. So we skip the 3. We just place 4 above. And we're now back up to the final node to consider. Oh, it doesn't get considered at all. Well, there we go. We were minimizing at the level above, and we'd already got a 1. And that maximizing branch there, the 4, goes down to the 4. So it doesn't really matter what's over here. This is at least 4. Minimizing node has at least a value for 1. So choose that one. So we knocked off a whole branch there, right? And as you go deeper and deeper, you actually get more opportunities to knock off more and more branches. Particularly, this gets back to the move order thing, which I haven't really talked about yet. We're going to start talking about that next, is that the move order makes even more pruning because you've already considered the best, or what you think are the best branches. Okay, sweet. Now that we've got a good understanding of alpha beta pruning, this is where the rabbit hole really starts. What I'm going to do in the rest of the video is consider a number of the factors and try and get a real firm grounding of how much time and effort you're saving by using alpha beta pruning. Now there's 2 groups of factors I'm going to look at. One of them is the type of tree itself in terms of the branching factor and the depth. Now we'll just quickly bring up my page here, and you can see this is something which I can actually change in my code. So this goes to a tree with a branching factor of 3, and you can see that actually these things, even though it can make the dots smaller and smaller and smaller, gets wide pretty quickly. That was branching factor 3, level of 4. So what about trying 10? Even that's not up to chest level standards, right? And see what that looks like. It looks like that, right? Yeah. And I think the last one to look at would be, we can also affect the depth. Let's just go back to a normal tree, maybe a 2, and do a depth of 6. See how big that looks. There it is there. You can see I've cut it off a bit. So this program I'm using, we're able to consider all these possibilities, right? So at first glance, the more levels you have and the more branching factor, the more saving you're going to do, right? But this is to be proven and to be tested. Then we go back to the other set of factors, which is all about the move ordering. Now, I've sort of highlighted 4 possibilities there. There's a random one, right? Totally random. You do have a sense of, from the iterative deepening, you'll get a good sense of the move before you're actually considering the level one below. So you might get a sort of a nice ascending ordering or descending ordering, depending upon whether you're minimizing, maximizing, and then there's an optimized ordering where you actually get the child nodes actually are in the exactly right order. And these move order concepts, obviously people spend a lot of time trying to optimize them so that the search is most efficient. And I'm just going to do some testing and see what sort of impact it has on the number of nodes that you have to visit. Okay, so what we're going to do is, in this simple case, branching factor of 2 and a depth of 5, we're going to consider those 4 different ordering techniques of the leaf nodes and just have a look at what impact it has on the number of nodes you have to search. Now, overall, there's 31 nodes here, and let's see how many of those get cut out. This one is ascending order. That should be quite good in this case because it's a minimizing node. So if it considers all the lower value nodes first, the ones over here, that will be better. So let's have a look just to the normal process of stepping through. I'll do it very quickly. You can slow down the video if you like. I'm just pressing space to sort of proceed. Okay, so there's the final outcome. It's actually done really well. It's missed 11 nodes in total. Let's have a look how many leaf nodes. 1, 2, 3, 4, 5, 6, 7, 8 leaf nodes. Half of them basically haven't been considered, and they're probably the more computationally expensive things to look at rather than the intermediate nodes, which are just mins or maxes. So that's a pretty good result. So that was if the nodes were in ascending order. Just let me quickly pop over here into my code, and I think I can. There's this one. Run it again, and now that's descending order. See that? Let's see how many nodes it misses out this time. Right, so that's way worse. Right, we've only missed out 6 nodes, or 4 of the more expensive leaf nodes. So that is not as good by any means. So that gives you a sense, actually, the ordering is important. So the next one I want to quickly try now is the one with random order. Okay, here we have a random ordering. Let's see how many nodes this one drops. This one should be somewhere between the 2 other orderings. In fact, it performed worse than the descending. That's the luck of the draw. With the random ordering, you have to try it several times and see what different results you get. Now, I have one other ordering, which I call optimized ordering. Just let me load that up. Give me 1 second. Is that? Okay, here we go. And you can see it's kind of ordered them. Smallest numbers come first. And then I've made some attempt at switching for the, like here's a maximum node. Its children have been switched. Now, I'm not too sure I've done the 100% the right thing here, but I think it gives you some improvement in terms of the number of nodes you're able to chop off. So let's give that a shot and see what it actually does in real life. Okay, 18 nodes. So it's chopped out 13, which is the best result we've had so far. So that extra little optimization is gives you even further improvement, right? So I think that gives you an idea. We've got 4 move orderings or node orderings, and this optimized one where basically if it's a minimum node, you want the child you look at first to be the lowest, and if it's a maximum node, you want the child to look at first to be the highest. That's kind of the general logic to think in terms of it. Now, before I move on to a little bit of a statistical analysis, I just want to show you one more example of why branching factor matters. Okay, as you see, I'm just going to set it up with a branching factor of 10. It's too wide now. I'll drag it across and you can see it processing. It's doing it automatically now. Every like 20th second or so, it's doing a new node. And look what happened. It actually just skips so many things. 30 nodes in total out of 111. Right? You can see, because what's happened is that this is looking to get a minimum value. It has to, unfortunately, search all those first 10 nodes here. And then as it then goes across, 19, no good, forget it. 29, no good, forget it. And obviously 39, 49, so on. And you go back onto the node. So you can see that we've only had to consider 30 out of 111 possible nodes. So that really gives you a sense of how much improvement you're going to get as the branching factor improves, gets bigger, and also as you go deeper. So I thought that would be helpful. Anyway, that's really good. What I'm going to do now is I'm going to go away and run a lot of simulations, different branching factors, different tree depths, using those 4 different sorting methods for the leaf nodes, and particularly for the random one, I'll have to run it a few times to sort of get a stable figure. And then we'll have a few nice charts to look at, which will tell you how much time you save using alpha beta pruning in all these different move ordering environments. Okay, so I've done that, and what I found with my little Python code, it was so interlinked with Graphviz and Pygame, I couldn't actually get it to go very many plies of depth. So what I thought I'd do is I'll just give some very brief results here, showing sort of analysis at low level depth levels, and I can see myself getting another video out of this topic. So what I'm going to do here is just quickly show these charts I've come up with. I've done them in LibreOffice. So here, this first chart I'm showing you this is using just a branch factor of 2, just a binary tree, and then the different percent of leaves visited for different ply. And you can see it goes down to just visiting a few percent of the leaves at a ply 14 or 15. And there's the 3 ones, random, and then sorted in the appropriate order, and then optimized, where I've actually tried to put the children in the relevant order. And you can see that, so you, first of all, you benefit a lot just from random, right? You're already covering like 15% of the leaves, and then you do even better, sort of another order of magnitude better if you do some form of sorting or optimization, which is where the extra strength is coming from in the chess playing engines. Scroll down to the next one. This is a branch factor 3, same type of analysis. Could only get this to 10 ply before my code broke. Pretty embarrassing. So say same thing, right? You really, the number of leaves that you visit drops off very quickly, and ordering the moves in is actually makes it even better. I did a 10 ply. 10 ply falls away even more quickly, even at 5 ply. If you've done some optimized version, you're just looking at a couple of percent of the leaves, right? Which gives you, once again, several more ply of depth when you're doing your analysis. And then here is like, I've just done sort of the cross-reference at 5 ply, and you can see this is what I was trying to get at, that the more branches you have, then the more opportunity for alpha beta pruning, really carving out lots of nodes that you don't have to look at, and therefore you're much stronger. So what I will do is I'll just leave that there for today, and I'll come up with another video in time. But I think I've demonstrated pretty clearly how much more powerful engines are. Alpha beta pruning, everybody's had that, and then these different ways of ordering the moves at very high branching factors, just 20, 30, whatever the number is, you can really just totally ignore a whole swathe of the minimax search tree and be much more powerful. So you saw that in the video on disordering effectively the move ordering in Stockfish. Effectively you get an extra, I think 300 elo is what I came up with. Okay, so I didn't quite get to the end of the analysis I wanted, but I hope that video was sort of interesting and instructional in terms of if you're looking at your own chess engines, or just understanding how powerful engines are, and the importance of different factors in the chess engine technology. Thank you very much for watching.